Good morning. Thank you for the introduction. I am Andrea Marcucci. I'm a PhD student from Polytechnic di Milano. I am collaborating with a startup company named Infra, and we are working on a project in introducing a new maintenance intervention for existing tunnel linings. And the aim of this presentation is to introduce a new testing methodology for the assessment of the plastic state of concrete. Okay. So this is the project we are working on. As you can see, this system takes care of the entire maintenance of tunnels, starting from the head of the system, where you can see a scraping device that is able to remove a thin layer of the existing tunnel. Then, thanks to the hydraulic jacks, the mold can be placed under the scraped surface so that concrete is casted, casting a tunnel lining segment, after which the jacks push toward the scraping devices, scraping a new surface of the tunnel, and then the jacks pull again the mold, placing the mold again under the scraped surface. And in this movement, the mold slips again concrete. So we can we name this like a slip forming process for the maintenance of existing tunnels. This slipping of the mold happens when concrete is still in its plastic stage, so in the plastic state, so before the hardening of concrete. To assess the feasibility of this methodology, we started from the small scale testing, and this was made thanks to the use of a robotic arm that is commonly used for 3D concrete printing. In this case, in the nozzle, a tunnel-shaped mold has been mounted in order to give the shape during the extrusion. As you can see, there are some similarities with this technology with 3D concrete printing, especially on the material requirements. As a matter of fact, the material must be buildable in order to start the slipping of the mold, in order that the segment can sustain its own weight. And then we have moved to the larger scale. So in particular with one lay tunnel scale. In this case, we have also built a external mold that is simulating the existing tunnel, and then the internal mold is mounted on top of a steel frame that moves on the rails. So the internal mold is placed below the external mold, concrete is casted, and then when it's ready, the mold starts slipping. And this is how it works, so that the mold moves, extruding tunnel segments. And in particular, as you can see, this movement happens when concrete is not yet in its hardened state. So it's important to understand the right time at which the mold starts slipping. And for this reason, we have introduced this new testing methodology. So based on shear box tests and tensile dog bond tests, both the tests work with one half of the sample that moves against the other. So in particular for the shear box test, this half slides against the fixed one, generating shear stresses in this cross section. Whereas for the tensile test, the one half moves far from the other, generating tensile stresses on one of these cross section with reduced area. The movement is generated by a motor that moves with constant velocity. So 0.1 millimeter per second for the shear test and 0.05 millimeter per second for the tensile test. Then an LVDT is measuring the displacement during the test, and a load cell is recording the load required for the movement, so that the output of the curve will be a load versus displacement, and it is processed in order to obtain the stresses from the load. So the final output of the tests will be the stress displacement. This is the mix design adopted by during the experimentation. So we have 600 kg per cubic meter of binder. There is made 30% of CSA and 70% of Portland. 1400 kg per cubic meter of aggregates. There is mainly sand with a maximum diameter of 4 millimeter. In this case, the aggregates are different compared to the real scale application. We have just adopted a new size distribution for the tests. Water binder ratio, there is 0.35, super plasticizer, and then 3 quantity of retarders. So at the end of the day, we have 3 different mixes, and this was useful to understand the effect of the retarder in the delaying the setting time, so the time at which we want to move the mold to slip and to extrude the segments. And this is the mixing procedure. We first add the powders like aggregates and retardant, then we wet the aggregates, and after which we we add the binder, and at this time the clock starts. We have also performed some Vicat tests in order to establish which were the right testing time according to these premixes. In particular, this is the testing time window we have selected, so from 45 minutes to 90 minutes, testing every 15 minutes. We don't go after 90 minutes because the material otherwise is completely rock solid and out of the scope of this experimentation, and we didn't use higher retarders compared to 1 gram per liter, because otherwise the material is still too fluid even after 45 minutes. And then we have averaged the curve because we have tested at least 3 times at each testing time for each mix. So this is an output of the shear test curve. So for example here at 60 minutes, and we are in particularly interested in the peak stress and also on the stored energy. That is, as you can see here, the area below the curve until the peak stress. In particular, to make it independent by the displacement, we have divided the value of the energy for the displacement corresponding to the peak, so obtaining a stored energy per unit displacement. So these are the results for the retarder at 0.8 gram per liter, and as you can see, there is a clear distance between the 75 and 90 minutes curves compared to the first two. In fact, there is almost a phase transition, so that at 75 minutes the material is almost solid, whereas at 45 minutes is plastic, as you can see here from the picture, but with limited strength that starts developing only at 60 minutes, where the material is still in its plastic stage. As you can see, there is a exponential increase of the strength between 60 and 75 minutes. There is a sudden increase of the strength with quite a high variability of the results. That is due to the fact that there is a very large increase of the strength in a very limited time window of only 15 minutes that made difficult to obtain the same repeatability of the result that we got at earlier times. And this is valid both for the stored energy and the peak stress. This is the influence of the retarder. So at 60 minutes, we can see a clear dependency of the strength with the retarder. As a matter of fact, the higher the retarder, the lower is the strength. Whereas at 75 minutes, we have no longer the effect of the retarder on the development of the strengths. In fact, as you can see from the curves, they are pretty much close each other. And here you can better see from the stored energy for different quantity of the retarder, there is a clear linear dependency of the energy with the quantity of the retarder at 60 minutes, whereas at 70 minutes there is no clear evidence of this dependency. So we can say that it's too late for the shear strength to have any effect on the retarder quantity. And again, by looking at the peak stress, almost linear trend of the peak stress with the retarder quantity at 60 minutes, no longer the effect at 75 minutes. Then for the tensile tests, we have processed more the output of the test. We have computed also the strain, so to obtain a stress-strain curve. And we obtained the strain simply dividing the displacement measured during the test for the initial length of the sample. And this is what we got from the tensile tests. So we were interested again on the peak stress. And then we have also tried to measure a parameter that belongs to the solid state, but we measured also here in the plastic state the Young modulus by linear interpolation of the first branch of the curve until the peak stress. So these are the tensile tests results, and again at 75 minutes there is a clear distance, a clear increase of the strength compared to 45 and 60 minutes. But differently from the shear test, we can see that the increase of the strength is a little bit delayed, because at 60 minutes there is no increase of the strength as was happening for the shear strength. In fact, the two curves are very close. But we can still see an exponential increase of the strength if we consider the 75 and 90 minutes. In fact, at the beginning, the strength is not increasing, so there is a flat increase, and then an exponential increase of the strength, both looking at the Young modulus and the peak stress. And this is the influence of the retarder. So it seems here now too early at 60 minutes to see any effect of the retarder on the strengths, whereas we can see instead at 90 minutes the effect of the retarder. In fact, for 0.8 gram per liter of retarder, there is an order of magnitude of difference compared to the other two quantities of the retarder. And this is more explicit by looking at the Young modulus. In fact, no clear trend at 60 minutes, whereas we can see instead a dependency of the retarder, as for the least quantity of the retarder we have the double of the stiffness compared to the other two quantities for 90 minutes. And again, no clear trend here, because it's now meaning that the peak stress is increasing with the quantity of the retarder, whereas a clear dependency on the least quantity of the retarder, as the peak stress is one order of magnitude different compared to the peak stress at 60 minutes if we look at the peak stress at 90 minutes. So, concluding, a new testing methodology consisting of shear box and tensile dog bone molds has been introduced with the aim of studying the intermediate state of concrete between fresh and solid state by measuring shear tensile strengths. Thanks to this test, it's possible to study the plastic state of the material. An exponential increment of the strength of time has been observed both for the shear and the tensile tests. Vary the quantity of the retarder. Of course, it varies the plastic time window of interest. And the increment of the shear strength is faster than the tensile strength. And this may be due to the faster development of the compression stress that influence the shear strength of the material. For shear test, after 75 minutes, the retarder has no longer any effect, whereas at tensile test, the retarder has still effect at 90 minutes. So, thank you for the attention.
So, I would ask a question. So, how much do you need to do this job?
For the aggregate. That's a good question. Actually, we didn't investigate the possibility of any influence of the aggregates on the results, and it's something that we might take into account maybe by testing with different size distribution, because we don't have any clear idea of this dependency.
The second part of that is, so based on your results,
Yeah. Looking at these tests, actually we can say that in between 60 and 75 minutes may be the right time. Actually, we have seen that there is a sudden increase of this strength that can be due to the CSA cement in the binder, and in fact for this reason we might have to increase, so to reduce the time interval during the test, especially focusing on the time window between 60 and 75 minutes in order to be more precise on the time at which we have to slip the mold in order to understand bending that time. Sorry, I didn't understand. Can you please?
I'll take a lot. Given some of the variability that you showed in your data set, phenomenon like you described, is the intention to take these tests and make field?
Okay. No, actually, these tests are complicated to make on field. So, and again, the variability of the result can be due a lot on temperature, because we have seen that this mix is very variable on the temp, so has a lot of sensitivity on the temperature. So that can be another issue that I didn't show here in the presentation. So yeah, maybe it's better to try to develop a on-site test because of this reason again. Yeah.
We have to have the data for it.
Thank you for the question.